Good morning and welcome to these video lectures on advanced data structure. And today we'll be covering the red-black tree. This is the second part of this red-black tree, and we'll cover in details. And this is Dr. Gunamani Jana, Professor in Computer Science Department of Roland Institute of Technology. The red-black tree, these are another type of balanced binary search tree. We already studied the VL tree, one of the balanced binary search tree. This red-black tree, it is one of the balanced binary search tree. One extra parameter is introduced here, that colors. So two color nodes are there. It can be red node or it can be black node. It is a self-balancing binary search tree that makes use of these colors to maintain the balance. So with the color, we maintain the balancing. There is nothing to worry about other things. Whether you go for the insertion, deletion, or searching operations. So it is only with these colors and what are the properties using that one, we maintain these things, self-balancing. Hence, during the red-black operations, the memory uses only one bit of storage for this color. Okay, memory uses one bit of storage to accommodate the color information of each node. Extra one bit we use it. In red-black tree, it is also known as the arbitraries. These are different conditions. You see an example here. This is a example of red-black tree. Here, the starting node, we call it the root node. They are the children of that one, children. And this node, the leaf node is represented by this leaf node here. It's clear? And the properties, if you consider the properties, every node is either red or black. See, the node is either represented in red, black color or red color. Then second one, the root node must be black. We cannot make the root node as the red color. Right? Next one, all null nodes, they are also black. These are the nil or null, whatever you say. These are also black. The red node doesn't have a red child. See, if this is the red node, it cannot have red children. So it can have only black children. Right? But a black node can have red children or it can have combination of red and black. These are- Then the fourth point, every path from a given node to any of its leaf node, the number of black nodes should be same. See, if I start here, this point to this point, there are one to two number of black nodes. If I start from this point or this point to leaf node, it is only two number of black nodes. I start from this point to this point also, the number of black nodes to here also the black nodes are two. So these are the conditions we have to remember. And this table I am not using right now. Once we become expert, only I give some notation. EI used as a parent, GI used as a grandparent, U as uncle, and the node you are inserting. Okay. The basic operations in the red-black tree, we can go for the insertion, deletion, search operation. Okay. So we start with the insertion operation. And how do we insert? Say insert means first we check whether the tree is empty. There are two cases. Case one, simple. Case two, again two options we are having. We'll go for that one. Case one, check whether the tree is empty. That is, if not a single node is there in this tree, make the current node as the root node and color the node to black. If it is empty, that means the root node cannot be red, it should be black. Because by default, when you are adding a node, it should be red color. And the first, because you are adding it should be red color. But if it is the root node, so it must be black. Is it clear? So if the root is empty, we add a node and this is the first node or the current node and the color must be black. Clear? So this is chapter close, the case one. Case two, if the tree is not empty, first already some nodes are there. So we create a new node and color it red. So here are two problems or two conditions. If the parent of the new node is a black, suppose I am creating a new node or adding a new node. So the new node is red color. The thing is that if the parent of this new node is black, we don't have any problem. The operation tree is left as it is, so it is allowed. But if the parent of this new node is red, if the parent is red, then again we have two conditions. If the parent of the node is red and the sibling means it is uncle and parents brother, younger or elder or whatever you say. If the parent's brother, the sibling or the uncle is either black or red, okay. So I'm telling you that if the parent color is red and if the sibling is either black or does not exist or null is also by default black, right? So if the parent is red and uncle is black or uncle is null, in that case, what we do two things. We go for the rotation and the recoloring. Remember one thing. So while we are adding a new node and it is not the root node, and if the parent is red color, because if the parent is black, we don't have any problem, you add it. So the operation is such as we don't have problem. It is balanced. But if the parent is red and its uncle is black or null is black and black is black. So in that case, what we are doing, we have to recolor and also go for rotation, right? Now the second option is the we are adding the empty, it is not empty and there is the root node, everything is there. The parent of this new node is red and color of the sibling is also red. That means your father is parent is red and your uncle is also red. In that case, only recolor the parent and also the sibling and also the grandparent. That means you cannot make all red or black like that. So father and uncle color will be changed, and accordingly the grandfather color also will be changed. So this is the cases we have to remember. Okay, it's enough theories. Now let us go. Uh, we see some cases. In that case, how we do all things. Now let me start with a very starting one. So how the condition we apply. First, what I told, if the parent is red and uncle is black, that condition will see. First we saw the tree. First, I want to insert my first node. The tree checked, it was empty. There was no node. So I added a node and the key is 1 for this node. So this is declared as the root node and the color will be black as per the condition one satisfies. No problem. Now I'm going to add one more node and the key is 2. Now 2 is larger than 1, so it will be in the right hand because it has to follow the binary and binary search tree, all the condition it has to follow. Now the tree is not empty, so we create a new node and add the next integer with color red. So I added 2, and the color to be red by default. Tree is added, it is 2. So this is also not deviating. There is no problem till now. So the tree is not empty. So we created a new red node with the next integer. But the parent of the new node is not black. Suppose in this case, what will happen? In this case, so I want to add one more node. So I added 3. When I added 3, because all the new node is by default red color, I added 3. But what about the parent? The parent is red. So this is the parent and this is the grandfather parent. This is the P and this is GG, the grandparent. So what is the sibling? That sibling means it's if this is the candidate, if it is father, then somebody should be there, his uncle. Okay. If uncle is not there, nil is there. So uncle is black or nil is black. In that case, what we do? We have to go for rotation and also recoloring. Okay. How do we rotate it? See, 1, 2, 3, 2 will go up and 1 will come down. See, 2 will go up and 1 will come down. So these two are red and this is black. Understand what I have done it here? It was there like this. And in this case, I have to go for a rotation. Which rotation will right rotation is not possible. You have to go for left rotation. In this rotation, 1, 2, 3. So 2 will be up and 1 will be down. That means 1 will be the left child of this root node 2. 2 become the root node and 1 and 3 become the child node. Then the color of 1 and 3 will be red and color of the root node will be black. Okay. Same thing I did it here. Now suppose I want to add one more node, say with 4. So I added 4. So in this case, this is the parent. This is the parent. And this is the uncle. So parent is red and uncle is red. What is the case? The traditions can violate the red because it is not possible because the parent cannot be red. Okay. So the tree once second violates the red B balance tree. So we check for the parents sibling node color also. This is also red. So we just recolor. There is nothing to worry of all these cases. Then what we'll do? So 4 will be red as it is. 3 and 1 will be black. And we are supposed to recolor this one, 2 also, because it is the root node, we cannot recolor, it will be black as it is. Black, black, we don't have any problem. Black, red also don't have any problem. But red, red, we have the problem. Suppose I want to add the next element as 5. When I added the next element 5 here, then what is the parent of this one? Parent is 4. It is also red color. And what about the sibling? The sibling here, it is nil, mean black. When it is a red parent and a black uncle, so in that case, what we do? We have to go for recoloring and the rotation. Okay, what is the rotation? 4 will come up, 3 will come down. So 2, 1, 4, 3, 5. 2, 1, 2, 1, 4, 3, 5. It came. And what is the recoloring? So these 3 and 5 at the same level will be red color and 4 will be black color. It's okay. Up to this it is successfully inserted. Suppose I want to insert another element 6. So I added 6 here. While I am adding 6 here, the parent color is red. Parent color is red. And the uncle color is also red. In that case, what you have to do? So we have to recolor only because both are red means you have to recolor and some rotation will recolor only we do. In that case, what I do? So this is the red. These two will be turned black and the parent for the color also will be turned red. Now it is there. We don't have any problem. So if you check the condition here, suppose you want to add one more element 7. 7 I added here. When you added 7 here, then 7 is the right side of this one. So parent is red and sibling is black. Parent red and sibling is black. So in that case, what you have to? We have to rotation and recolor. Two things we have to apply. Then what is the rotation? 6 will go up and 5 will be the child of 6. So first we do 6 go up, 5 and 7 is there. These are red. This is black. This is the red. So all the things are there. Now we have successfully inserted and you see, now I want to check what is the number of black nodes from 2 to the leaf node here. It is 2. From 2 to this one also it is 2. And from 2 to this one also it is also 2. So 2 number. So all are conditions satisfied. And check root node is black. And black can have a black and red child, no problem. Red can have only black children. Red cannot have the red children. The black can have red children. So all the conditions satisfied. Now suppose I go for the deletion operations because two operations, major operations are insertion, deletion, and search. And we search it for searching a color is not important. Now, the deletion operations on the red-black tree must be performed in such a way that it must restore all the properties of a binary search tree, BST, and also red-black tree. Because red-black tree by default it is a binary search tree, so it has to satisfy the condition of BST and also satisfy the condition of red-black. That means what are the properties we applied for insertion, same property also is to be allowed to the deletion. Now there are two, three cases. If either the node to be deleted or the node's parent is red. If the node is red or its parent is red, whatever things are there, just delete it. Case one. Let us see. The first case, I want to delete 4. I want to delete 4. If I delete 4, it is a red. It is a red one. The parent is not red, but it is red. So in that case, just delete it. If I delete it here, then what will go next? Which one will go up? 4 deleted means 3 cannot come here. That is not like that. So in that case, what we'll do? Uh, in that case, what we'll do? See, this 5 is coming up, 3 becomes the left child, 6 becomes the right child, and so and then we go for the recolor. Color here it is red, here it is black, here it is red. Suppose I want to delete again because I deleted 4 and I want to delete 5. If I want to delete 5 means again it is a red, I can delete, I don't have any problem. When you deleted this one, then what will happen? 3, 6, 7. So 6 will go up and 3 become the left child and 7 become the right child. Just what are they? Sort it and put it there in the top. Easy. It's the same thing we have done it, Come and check it here. So when I have to delete 4, I deleted this one. Then uh, this has gone up, right? So 5 was successfully deleted. So the new tree become arbitrary count 21637. Now, suppose I have to delete 3. If I have to delete 3 from this tree, applying the binary search deletions, we deleted node 3 normally as it is a leaf node and we got a double node at 3. So what happened? When you deleted this one, 3 you want to delete, it is a leaf node. So you delete it. So once you delete it, you are getting a null node like this. Okay. If you apply case 3 deletion as a double black sibling node is black and the child nodes are also black. Its sibling is black and the child is also black. Here, its sibling is black and this is also black. In that case, why do black? Here, we remove the double black and recall the double black as parent. So, this I have to remove and this 6 color I have to recolor. That means 6 will become black and this will become red. So, this is all about this is one example I have given how to insert and remove the red black tree. And still you can refer a number of examples. By solving this, you can understand. Thank you for watching this video. Once again, if you like this video, please do share with your friends. Thank you.